Welcome. Today we're going to cover covalent bonding and we're going to learn how to draw Lewis dot structures. You've already learned how to draw Lewis dot structures for ionic bonds. Today we're going to cover Lewis structures for covalent bonds. First, you need to learn some terms. The first term that you're going to learn is called NASL, N-A-S-L. And NASL, the NASL method, is a way of drawing covalent bonds or finding out how many bonds or how many lone pairs there are going to be in a bond. It's the best way I've found to systematically count the number of electrons and the number of bonds that you need. So the first thing we're going to do is learn what these letters mean, NASL. Don't worry if you don't get it at first. We're going to work some examples. The first thing you need to do is just write down the terms. The first term is N for needed electrons. And the needed electrons basically means that we're going to follow the rule of 8 or the octet rule. All atoms want to have 8 electrons in their outer valence shell. In ionic bonding, we did that by gaining or losing electrons until the shell was either full or we lost a shell and went back to the previous full shell. Now we're going to get that way by sharing. So every atom wants 8. So if we've got 5 atoms and they each want 8, that's 5 times 8 is 40 electrons. There are some exceptions. Hydrogen is too small to have 8. Its shell only holds 2. And beryllium and boron are kind of oddballs. Beryllium will want 4 and boron will want 6 when it's covalently bonded. When it's forming an ionic bond, we just follow the normal rules. But beryllium and boron are not very common. We won't see them very often. But we'll see hydrogen a lot. So anyway, the needed electrons. A stands for available electrons. Each atom brings its valence electrons to the molecule. So we're going to add up the valence electrons that are provided by each atom, and that's how we calculate the number of available electrons. When we subtract needed and available, we end up with the number of shared electrons. So the shared electrons is equal to needed minus available, and that's how many electrons are actually going to participate in bonding. The last is L, leftover electrons, or if you're counting pairs, they're the lone pairs. We find that by subtracting available minus shared. So these two math equations here, we just subtract the numbers right above. So for shared, we have needed minus available, and for leftover, we have available minus shared. So let's get on to an example so we can see what these terms really mean. The first example is carbon tetrachloride, CCl4. The first thing we need to do to draw our Lewis structure is to place the center atom. There are 3 rules that we're going to use to determine which one is the central atom. The first is to look at the atom that's all by itself. Carbon is all by itself, and there are 4 chlorines, so most likely carbon will be in the center. But we can also check the electronegativity, and it's usually the one with the lowest electronegativity. Carbon also meets that rule. So we'll put it right in the center. There's a third rule, and that involves hydrogen. Hydrogen can never be in the center because hydrogen can only handle 2 electrons or 1 bond, which means it can only be at the end. It can never be in the center. So now that we have carbon placed, let's go on and place our other 4 chlorines around the carbon atom. So we need to look and see if there are any exceptions present before we do our math. I don't see any hydrogens here or berylliums or borons, so there are no exceptions. We have 5 total atoms and each wants 8. So 8 times 5 will give us 40 electrons. That's how many we need to make everybody happy. I'm going to divide it by 2 and do my math in pairs because that's easier for me. So 40 electrons means that I have 20 pairs of electrons that I need to complete this molecule. Now the next thing we need to do is figure out how many electrons we actually have available. Carbon is in group 14 or 4A, so it has 4 valence electrons. Each chlorine is in group 17 or 7A, so each chlorine brings 7 electrons to the molecule. So we have 4 plus 7 plus 7 plus 7 plus 7. I did that as 4 plus 7 times 4, and I ended up with 32 available electrons. Divided by 2, and I have 16 pairs of available electrons. Well, I need 20 pair, and I have 16 pair, so I'm going to need to share some electrons. So sharing I calculate the shared electrons as 20 minus 16, as we see right here. 20 minus 16 pair means I have 4 shared electrons. Those will be 4 pairs of shared electrons. Those will be my bonds. So there's a pair, there's another pair, there's a pair, and there's a pair. So we've put 4 pairs around our central atom, bonding to each of the chlorines going around in a circle. Next, we need to look at our lone pairs. How many are not participating in bonding? So we have 16 pairs available, and we're only sharing 4, so 16 minus 4 means we have 12 lone pairs. The rule for placing lone pairs is to place them around the outside of the outer atoms, keeping in mind the rule of 8. So no atom can have more than 8, and every atom wants to have exactly 8, as long as it's not one of those exceptions like hydrogen. So this chlorine here already has 2, so let's go on and add another pair, and another pair. So we've used up 3 of our lone pairs, and now chlorine has 8. We'll go on and do that for the other chlorines. So there's 3 more pair, that's 6, 7, 8, 9, 10, 11, 12 pair that we've placed. So we placed all 12 of our lone pairs around the outer chlorines. Now if I'd had any left over, which I didn't this time, I would have put them on the central atom. But this time we didn't need to. The next step is to look and see if we've satisfied the rule of 8 for every atom in the structure. So we'll put circles around each of these atoms and around the carbon in the center. And we'll count and see if we have 8. 1, 2, 3, 4, 5, 6, 7, 8 for this chlorine, 8 for this chlorine, 8 for this chlorine, 8 for this chlorine. And lastly, let's look at our carbon. 2, 4, 6, 8. So carbon also thinks that it has 8 electrons, so everybody is happy here. Now these shared pairs right here, the ones that are circled on the outside and the inside, these electrons being shared get to be counted by both of the atoms that are sharing them. So right here, chlorine and carbon both get to count these as part of their 8. Also, there's another way that we draw shared pairs. When we're drawing a shared pair, rather than draw it as a pair of electrons, we can draw it as a dash. And from now on, I'll draw shared pairs as a dash. So let's go on and change these to dashes all the way around. And just remember when you're counting electrons that each dash represents a bond, which is a shared pair. So each dash is 2 electrons. The last thing we're going to do is we're going to look at the bond type. We want to see what the carbon-chlorine bond is. So to do that, we look at our electronegativity chart. The higher, the chlorine, is 3.16 minus 2.55 for the carbon, and we end up with a difference in electronegativity of 0.61. That's more than 0.3, which means that this bond is very polar. The carbon-chlorine bond is very polar. Now that doesn't make the molecule polar, but certainly the bond is polar. We'll look at the polarity of the overall molecule tomorrow when we look at the shapes of molecules in 3 dimensions. Now let's look at phosphorus trihydride. That's its covalent name. So we have pH 3. The first thing we need to do is find the central atom. The lowest electronegativity, just barely, is phosphorus. It's also the only one by itself, and it's not hydrogen. So it will go in the center. We'll place the 3 hydrogens around it. It doesn't matter where you put them, because if we rotate the molecule around, it would look the same with the hydrogens on top. So we can always spin the molecule and make it look the same, whichever direction we put the hydrogens. We look to see if there are any exceptions. Well, of course, there are 3 exceptions, the 3 hydrogens. So when we're calculating our number of needed electrons, we're only going to count each hydrogen as 2. So we have 2, 2, and 2, and 8 for the phosphorus. So 8 plus 2 plus 2 plus 2 is 14 electrons. We'll divide that by 2, and then we end up with 7 pairs. So we need 7 pairs of electrons to make everybody happy. Now, how many do we have available? Well, phosphorus has 5 because it's in group 15 or 5A, and each hydrogen has 1. So 5 plus 1 plus 1 plus 1 is 8, which means we have 4 pair actually available. Those are the valence electrons. Well, if we need 7 and we have 4, we're going to have to do some sharing. 7 minus 4 gives us 3 shared electrons, 3 shared pairs of electrons, pardon me. So if we have 3 pair that are shared, we can draw 3 bonds between the phosphorus and the 3 surrounding hydrogens. Next, we're going to calculate our lone pairs, and we're going to do that by available minus shared. So 4 minus 3, that gives us 1 lone pair. Well, hydrogen can only take a pair of electrons, and it already has one in this bond. So we can't put the lone pair around the hydrogen. We can't put it around any of the hydrogens. So it's going to have to go up here on top of our phosphorus. Remember, if we have leftover lone pairs, they always go on the central pair after we've filled up and met the rule of 8 for the surrounding atoms. It's the rule of 2, really, for the hydrogens. Now we're going to look and see if we meet the rule of 8 for everybody. Hydrogen has its 2 in this bond. Hydrogen here has 2, and hydrogen here has 2. And let's count the phosphorus electrons. So this dash counts as 2, 4, 6, and the lone pair makes 8. So everybody is happy. Let's also look at the phosphorus-hydrogen bond. The phosphorus-hydrogen bond, we start with hydrogen really is first, so 2.20, and the electronegativity of phosphorus is 2.19. The difference is 0.01, very small, which means that this is a non-polar bond between phosphorus and hydrogen. The next example is SO2, or sulfur dioxide, by its covalent name. The central atom will be the one with the lowest electronegativity, which is sulfur. It's also the only one by itself, so it makes sense it should be in the middle, and it's not hydrogen. So we'll put sulfur in the middle and put the 2 oxygens on either side. Next, we see if there are any exceptions present. I don't see any hydrogen or beryllium or boron, so no exceptions. So we can now just figure out our rule of 8. 8, 8, and 8. So that's how many electrons we need. 8 plus 8 plus 8 is 24. Divide by 2 and we have 12 pair. The number available, oxygen and sulfur are both in group 16 or 6A, which means each atom here provides 6 electrons to the molecule, 6 valence electrons. 6 plus 6 plus 6 is 18. 18 over 2 is 9 pair. So we need 12 pair, we have 9 pair, so we need to do some sharing. 12 minus 9 means that there are 3 shared pairs of electrons. Those are our bonds. So we'll put a bond here and a bond here, and, well, we've run out of atoms to bond to, but we need to put a third bond in. So our third bond we'll put between a sulfur and an oxygen, and now we have something called a double bond. And double bonds and even triple bonds are okay as long as we're not bonding to something like hydrogen. Hydrogen, remember, can only take 1 pair, and these 2 bonds constitute 4 electrons, 2 for each bond. So we can't have a double bond on a hydrogen, but it's okay here between sulfur and oxygen. Now let's calculate our lone pairs. Our lone pairs, 9 available, 3 used in bonding, so 9 minus 3 means there are 6 lone pairs that we have to spread out around the molecule. So we'll spread them on the outer atoms first, the 2 oxygens, keeping in mind the rule of 8. So we've already got 1 pair here in the bond, so there's another pair, and another pair. So now we have 8 electrons around oxygen. The other oxygen already has 2 pair, so it only needs 2 more pair, 4 more electrons. So we'll put the 2 pair here and here. Notice I didn't put them on top and bottom or on the side. I kind of spread them out diagonally, and that's just to represent the way it really looks. when we look at 3D models, you'll see that they tend to spread out as far apart from each other as they can without actually infringing on the bond over here. So let me count the lone pairs. I see 1, 2, 3, 4, 5, and that satisfies the rule of 8 for all of the oxygens. But I have 6 lone pair. So the leftover lone pair is going to have to go on the central atom, sulfur. Now let's look at each individual atom and see if it satisfies the rule of 8. So we've got 2, 4, 6, 8 here. For the oxygen, we've got 2, 4, and then each one of these bonds counts as 2, so that's 6, 8. And then lastly, we'll look at the central atom, sulfur. It has 2 here in that bond, 4 and 6 in that double bond, and then 8 for the lone pair. So we've got 8 electrons around sulfur. Everybody is happy. Let's look at the bond type for sulfur and oxygen. The SO bond, oxygen, has the higher electronegativity, so we'll put it first. 3.44 minus 2.58 for the sulfur. So the difference in electronegativity is 0.86. That's above 0.3, so this is a polar bond between sulfur and oxygen. The next example is HF, or hydrogen fluoride. Hydrogen fluoride is a binary compound. There are only 2, so there's really no such thing as a central atom. The lowest electronegativity is hydrogen, but it couldn't be in the middle. But since we've only got 2, it doesn't matter. So we'll just put hydrogen and fluorine right next to each other. Are there any exceptions? Well, hydrogen is an exception, so it's going to need 2 electrons, and fluorine's going to need 8. So 2 plus 8 means we need 10 electrons. Divide by 2, and that gives us 5 pair. The number of available electrons is less than that, though. Hydrogen comes to the table with 1, and fluorine brings 7 to the molecule because it's in group 7A. So 1 plus 7 is 8, which means we have 4 pair of available electrons. So if we do our math with the pairs, 5 pair minus 4 pair means we're going to share 1 pair. So we'll go on and draw that bond in right here between hydrogen and fluorine. If we look at the lone pairs, 4 pair available minus 1 shared pair, and that leaves us with 3 lone pairs. We can't put any around the hydrogen because it's already formed a bond, and it can only take 2 electrons. So the other 3 lone pairs will have to go around the fluorine like this. We put our circles around the 2 atoms so that we can check for the rule of 8, or the rule of 2 for hydrogen. It's got 2, and fluorine here has 2, 4, 6, and 8. So everybody is happy. Let's look at the HF bond. The bond between hydrogen and fluorine. Fluorine's the highest. It's usually shown as 4. Our table shows 3.98 for electronegativity, minus 2.2 for the hydrogen, a whopping 1.78 for the electronegativity difference. Well, generally 1.7 is considered the upper limit for a polar covalent bond, so this is actually verging on an ionic bond here because the electronegativity difference is so great. But we're going to call it polar since we're studying covalent bonds here. The last example is carbon dioxide, CO2. We need to find the central atom, and the lowest electronegativity, and the one by itself, is carbon, so we'll put it there, and then put the 2 oxygens on either side of it. Are there any exceptions? Well, there's no hydrogen, so no exceptions. We have 3 atoms following the rule of 8. That would be 8 plus 8 plus 8 are the number of electrons that will make everybody happy. So we need 24 electrons, which is the same as 12 pair. When we look at what everybody brings to the table, though, we find out we don't have 8 pair. Carbon here is in group 14. It has 4 electrons. And each oxygen is in group 16, or 6A, so they bring 6. So we have 4 plus 6 plus another 6, and that's 16 electrons, or 8 pair. So if we need 12 and we only have 8, we've got to do some sharing. So 12 minus 8 is 4. We have 4 shared pairs, so we'll put in one between between carbon and each oxygen, so there's two, but we still need to put two more bonds in. So we'll spread them out between the other surrounding atoms. So now we have a double bond on each side between carbon and oxygen. Now we'll look at our lone pairs. If we have 8 pair available and 4 shared pair, 8 minus 4 is 4. So we have 4 lone pairs to spread out around the atoms in the molecule. We start with the outer atoms, the 2 oxygens, and keeping in mind the rule of 8, we've already got 2 pair here, so each oxygen will need 2 more pair to have a total of 8. So I'll place 2 there and 2 over on the other side, and that uses up all my lone pairs, so there's none left over to put on carbon. Let's see if everybody's happy with the way this is. So 2 pair here and 2 lone pair make for 4 pair, or 8 electrons, so oxygen's happy. The other oxygen, a mirror image over here on the other side, has 2 lone pair and 2 bonds, a pair each, so 2, 4, 6, 8, it's happy. And carbon in the middle has 2 double bonds. Remember that each bond is 2 electrons, so we have 2, 4, 6, 8. So carbon has 8, and everybody's happy with this one. Let's look at the polarities and see what we've got. For carbon and oxygen, the electronegativity difference for these two, we start with oxygen, 3.44, minus carbon, which is 2.55, and we have an electronegativity difference of 0.89. So that's well above 0.3, so this is definitely a polar bond between carbon and oxygen. Now the molecule itself may not be polar, but we'll look at that when we look at molecules in 3 dimensions tomorrow.